Let's consider some additional properties of expected value. Suppose our random variable is always non-negative, and in most cases it will be, or if not, we can define a new random variable equal to x plus some constant, where the new random variable will be non-negative. If we know the expected value of x, what can we say about the probability of x being equal to any given value? So it's useful to keep in mind, nothing is important. So let's start with a simple situation. Suppose we know that the expected value of x is 0. So when trying to get insight into probability, it's useful to remember it pays to be discrete. In other words, if we can start out with a discrete case, we might gain some more insights. So in the discrete case, the expected value is the sum of the products of the probabilities and the payoffs. So by assumption, the values of our random variable are always non-negative, and because it's a probability, any probability is non-negative. And so the sum on the right-hand side consists of non-negative terms only. Since the expected value is 0, then all the terms of the sum must be 0. And that means if x is positive, then the probability that our random variable is equal to that value must be 0. Now remember, the sum of all probabilities has got to be 1, but most of these probabilities will be 0. The only one we don't know about is the probability that our random variable is actually equal to 0. And so that probability must be 1. Now, this shouldn't be too surprising, but it does have some very useful consequences. Let's consider the variance. Since variance is an expected value, let's consider what happens if the variance is 0. Now, remember, while we calculate the variance as the expected value of the square minus the square of the expected value, it's actually defined as the expected value of the square difference between the random variable and the expected value. And so that means the variance is the expected values of random variable z, which is the square of the difference. But because it's the square of the difference, that means that z is non-negative, and so our expected value is 0, and our random variable is non-negative, and so that means the probability that our random variable is 0 must be 1. And so the probability that the squared difference is 0 is 1. And so that means it's certain that for any value of our random variable, that squared difference is 0. And since this expected value is actually a constant, it follows that x itself must also be a constant. And so for any random variable x, if the variance is 0, then x itself is a constant for some value. Now, most of the time the expected value isn't 0 and the variance isn't 0. We can still consider non-negative random variables, and so the question is, can we say anything about the probability that x is equal to some value in these other cases? Now, intuitively, if x is non-negative and we know the expected value of x, then most of the values of x will be near that expected value, and very few will be much larger than the expected value. So again, it pays to be discrete. In the discrete case, the expected value is the sum of the products of the payoffs and the probabilities, and we'll assume this is a finite sum so we can split it at c, so we'll consider everything less than c, and everything equal to or greater than c. Now, first, we can omit the first sum entirely to produce an inequality. So if we lose that first sum, the right-hand side gets smaller, and so our inequality is going to be greater than or equal to. To maintain the inequality, we can replace x with a smaller value. How about c? And since c is a constant, we can remove it from the summation. Now, the sum of probabilities is just the probability that x is greater than or equal to c. And so, rearranging our inequality, we find, which gives us something known as Markov's inequality. Let x be a random variable where x is non-negative. For any constant greater than 0, the probability that x is c or greater is less than or equal to the expected value divided by c. For example, suppose you flip a fair coin 100 times. Estimate the probability that there are 80 or more heads. Now, we could try to calculate this directly. This is a binomial probability with n equals 100 trials and success probability 1/2. But let's also try to estimate that. So our expected value will be and so Markov's inequality gives us, and you get what you pay for. It didn't take us a lot of work to find this probability estimate, so we can guess it's probably not going to be too accurate. On the other hand, Markov's inequality is going to hold for any probability distribution where we know the expected value, and so it's a very general result, which might not give us very specific information.